Here's 2017, number 2. We've got a block being released from the top of a ramp. There's a mass of M, which is a flat part here, and then eventually it's going to collide with a spring. And everything is just, no numbers here, just everything is labeled what we would probably guess. It's released from a height h, and the spring constant of the spring is k, and that's all we need, right? That's all we got. So part A has a number 1 and a number 2. Derive an expression for the speed of the block just before it collides with the spring. Well, since this is all frictionless down here, the speed just before it collides with the spring is the same as the speed when it gets to here. So that's an energy exchange from gravitational potential to kinetic here at the bottom. I don't know what the ramp angle theta is, so I can't find the acceleration and take that kinematics route. It would have a constant acceleration down this ramp, but I can't figure out what that is without knowing what the theta is. So gravitational potential turning into kinetic. Please write that down. And so let's see, that would be mgh is equal to 1/2 mv squared. The m's cancel, so the speed of the block is the square root of 2gh. We've seen that expression. We've done that little game many times. Part 2. Is the speed halfway down the incline greater than, less than, or equal to 1/2 the speed at the bottom of the incline? Well, we can just figure that out. It's really a proportional reasoning problem. If the velocity is equal to the square root of 2gh, then the speed, velocity, magnitude of, at halfway down would be equal to the square root of 2g times h over 2. Or, in other words, the square root of gh. So the question is, they want to know, is the speed halfway down the incline greater than, less than, or equal to 1/2 the speed at the bottom? So is this greater than, less than, or equal to 1/2 of this? So let's just find 1/2 of that. So from this, just taking this velocity and dividing it by 2, I would get this, the square root of 2gh over 2. Now the square root of 2 part, I could call that like this, and this are the same thing. Divide by 2. So the difference between these two, the velocity at halfway down is the square root of gh, and v over 2 is the square root of 2 over 2 times gh. So it's not half, it's the square root of 2 over 2. It's the square root of a half. Since the velocity depends on the square root of the height. And the square root of 2 over 2 is approximately 0.7. So that means that this, the velocity halfway down, is less than half of this. You could show this work to justify that. You could also, if you just look at this and you want to use proportional reasoning and say, since the speed depends on the square root of h, then at halfway down, it's the square root of 1/2, which is about 0.7. In case you don't believe me, the square root of 1/2 is about 0.7. All right, B. Derive an expression for the maximum compression of the spring. So there, all the kinetic energy is going to turn into spring potential. And all of that kinetic energy, regardless of whether you use a 1/2 mv squared and plug this back in, it's going to get you back to this. The energy that we all started with at the beginning was this mgh. That's how much energy it has there. And the maximum compression of the spring, 1/2 kx squared. If you're wondering, like, how do you know that this is the maximum compression? Well, if all of this energy becomes all of this, if I set those equal to each other, that only happens when it's at maximum compression. Before that, that'd also be a little bit of kinetic energy. So if I set these equal to each other and there's no more kinetic energy here, that means it's all been absorbed by the spring. So looks like that maximum compression x is equal to the square root of 2 mgh over k. Just solving that for x. And in part C, let's see. To determine an expression of the time from when the block collides with the spring to when the spring reaches its maximum compression. Well, while the block is in contact with the spring, it will be in simple harmonic motion, mass on spring, and I know that the period of simple harmonic motion, mass on spring, it's right on your formula sheet, it's equal to 2 pi times the square root of m over k. Now that's the period of an entire oscillation. So the question here is really how much of this is the time that it takes to get to that maximum compression. And I'll try to convince you that what happens here is it goes from here to maximum compression, and then it would come back again, and if it were attached to the spring it would come back, and so on. So that's actually exactly 1/4 of the period from here to here. If we were going to graph that, you don't have to do this, but just to try to convince you, the position, if that was position 0, it would start to oscillate like this, and from here to maximum compression would be this, and that is exactly 1/4 of the period. So that's like the full period. You could say that if you wanted to. So the time we're interested in here is that full period divided by 4, which would be pi over 2 times the square root of m over k. 1/4 the period of the oscillation. All right. Okay, let's see what they're up to now. So they're gonna do it again, but now once the block gets to the flat part, there's going to be a resistive force, which is directly proportional to the velocity squared. They're telling us that the drag force, that's what I'm going to call it, is equal to, or is directly proportional to, with this constant of proportionality, beta times v squared. So they want us to write but don't solve differential equation that could be used to find the speed of the block. Well, that's a resisting force. So here, this is just classic resisting force differential equations here. That would be the only force acting on it because gravity normal force would cancel each other out. So mass times acceleration would be equal to negative of this, because it's a resisting force, so the acceleration and the velocity will be different directions, so that negative sign is necessary there. So that means that the acceleration, dv dt, is equal to negative beta over m times v squared. And that's it for that part. They just want the differential equation, they don't want us to solve it. And we know that every time we ever do differential equations, we're always starting from mass times acceleration, and then we're replacing this with either dv dt or maybe perhaps the second derivative of position. So that's it for that. And then in D, that was part 1. Part 2, use the differential equation to show that, and then they actually give the answer, so we just have to try to get to it. So that means we need to solve this. So let's try to separate our variables here. So the v squared would have to go to the other side, and negative negative beta over m dt. That's my separation of variables. And then we integrate. So the antiderivative of v to the negative 2 is negative 1 over v. That would be equal to negative beta over m times t plus c. And to solve for c, I know that at time 0, right when it gets to the bottom, we have, they're calling the velocity v sub 0. V is equal to v sub 0. So plugging 0 in here, that would knock this term out. And plugging v sub 0 in here, so c would have to be equal to negative 1 over v sub 0. You can write out another step there if you like. So that means negative 1 over v is equal to negative b over m times t plus minus 1 over v sub 0. And we have showed what they want, except they just multiply through by negative, because since every term is negative, so we can do that. Why not? So that's not a terrible differential equation situation to solve there. All right, not too bad.